Hello everyone, I'm Dr. Shen from University of Southampton. Today I'm going to talk about quantum-analogous mirrors of space-time non-separable structured powers. First, let's review the concept of quantum entanglement. There are two crucial characters of entanglement: non-separability and non-locality. The non-separability means the degrees of freedom in entangled state are non-separable. The mirrors of one particle will impact on another entangled particle. For example, the polarization entangled photons. The polarization is uncertain, but if you mirror the polarization of one photon as a horizontal polarization, then you immediately know the polarization of another is a vertical polarization. That's the non-separability of polarization. Such an interaction is non-local in quantum photons. That as a spooky action at a distance. That makes the quantum effect so weird. Well, in classical field, there's no non-locality, but we can still use the local degree of freedom in structured light to construct the non-separability. Namely the classical entanglement. For example, the vector beam as a space polarization non-separable state. Here is the example of the vector beam where the vortex phase and polarization in a beam are non-separable. The classical entanglement is very useful. We can use the quantum-like mirrors method to measure the quality of vector beam. And we can also use the similar mathematics to transfer the quantum mechanics method and the quantum communication method to realize the similar application, communication, metrology, cryptography by using classical non-separable structured light. Well, the above examples are basically the space-time separable solution. But there is still another interesting non-separable light, that is space-time non-separable powers. For example, the localized focus power solutions, and another one is a very interesting flying donut powers. The flying donut is a single-cycle toroidal topology as a propagation anapole excitation. How to measure the space-time non-separability is what my work is focusing. Let's take a look at the typical example of flying donut to start the work. The flying donut is a focused single-cycle toroidal pulse. That the structure can be involved from one cycle into 1.5 cycle upon the propagation, revealing the space-time non-separable structure. Another description of such interesting space-time non-separability is using the spatial spectral description. Equivalently, the space-time non-separable structure results into a very unique spectrum. That's the isodiffraction spectrum. The isodiffraction means the various wavelength components diffract at the same rate. The isodiffraction is more clearly demonstrated here. The left figure is a spectral distribution at a transverse plane, and the right one is the trajectories of various colors, the maximum position of various colors. As is seen that the various colors diffract at the same rate, and the blue light is always confined inside and the red light is outside. And we plotted the radial ratios of the maximum color position, psi, and the maximum intensity for the various monochromatic components, and also the total intensity distribution versus the radial ratio. As is seen that these parameters are all propagation independent, the Z independent, revealing the isodiffraction property, so that we can define two classical states to describe the interesting isodiffracting effect. The first one is the spectral state, lambda I state. That means the monochromatic component state of light of defined wavelength lambda I and with defined radial position of the peak intensity. And the spatial state is the total field state of light, located at the position with defined radial ratio of eta. The eta is the radial ratio, the radius over the constant radius, the R max. R max is the radius of the maximum total intensity. For an iso diffracting pulse, the spatial state and the spectral state are perfectly coincident. Each spectral state is located at corresponding radial ratios, and that the spatial state and the spectral state are non-separable, fulfills an entangled state. As a comparison, we also built a wideband logarithmic mode, the LG mode, that is superposed by many colored LG mode components. These two pulse has the same donut shape and the wideband spectrum, but the LG pulse does not hold a good space-time non-separability. As it seems, after focusing, the various color components can have different focus degrees. So the spatial and the spectral states are surely randomly separable upon propagation. So there are possible many crosstalk terms in the general space spectral state. How to measure the spectral and the spatial entangled state in an experiment? The first step is to detecting the spectral state. We can obtain the various spectral components by the filters for various wavelengths, and then find the maximum region correspondingly, and construct the classical field as shown in the gray band regions. For the spatial state, we do not need the filters. We should directly measure the whole field of the beam and record the various ring regions for each radius, and the radius is predicted by the ideal isodiffraction theory. Then we can get the functions of corresponding spatial state. The next step is the state tomography. Akin to the quantum state tomography, we calculated the inner product of each combination of spectral state and spatial state. The tomography matrix allows us to find each coefficient of the tensor product state. The coefficient are Cij for ideal entangled state. The Cij is non-zero only if the I equal to j. So that means the space-time entangled state is corresponding to a diagonal tomography matrix. Since we know that the space spectrum state can construct the density matrix and calculate the many quantum measure concepts to characterize our space-time pulse. First, we calculate the fidelity. The fidelity in quantum mechanics is a measure of similarity of a measure state to the ideal state from 0 to 1. And in our simulation, we set the ideal state as the ideal flying donut pulse, and so we can measure the similarity of our measured pulse to ideal pulse. We also calculate the concurrence and the entanglement of formation, the EOF, to quantitatively measure the degrees of non-separability from 0 to 1. The 0 means the state is purely separable, and the 1 means the state is maximally non-separable. Here are the results for an ideal flying donut and a flying donut with noise, and the wideband LG beam and monochromatic LG beam. The perfect flying donut is set as the ideal case. So the fidelity is 1. And after adding some noise onto the flying donut, the fidelity is decreasing to 0.6. That means there is still some iso-diffracting effect, but with some deviations. The wideband LG beam, we know that the is such about do not have the iso diffraction, so the fidelity is nearly 0. That means it has a very different spatial spectral structure. And the monochromatic LG beam is also fidelity is nearly 0. And the concurrence and the EOF of the flying donut is nearly 1. That means the ideal space spectral non-separability is ideal, is perfect. That is decreased for the noised flying donut, and further decreased for the LG beams. And as an extreme case of a monochromatic beam, the concurrence and EOF is exactly the 0. Such a spacetime non-separable pulse can be generated by a singular metamaterial array as a singular metamsurface. We just need a conventional planar wave and convert it into a radial polarized light by radial polarizer, and then converted the radially polarized pulse into the flying donut by our designed singular metasurface. We measured our experimentally generated flying donut pulse with a fidelity of 0.8, so that we can argue our experimental flying donut pulse has a very good quality. In conclusion, we propose the state tomography method, the quantum-like method, to measure the space-time non-separable pulse. And the degrees of space-time non-separability can be quantitatively measured from 0 to 1. And the space spectrum state tomography method can open the numbers of applications. For example, we can use our classical space-time non-separable pulse to make quantum-like cryptography and quantum-like communication and quantum computation. Thanks for your attention.